Hi, everybody, and welcome to the second lecture in my mini tech series on a lecture on special relativity. So now on in this second lecture, basically we're going to focus on closing out the luminiferous ether. So you might have remembered from a previous lecture that the luminiferous ether, it's a tough thing to say. But the luminiferous ether was something that physicists were obsessed with because they believed that this was the medium that any sort of electromagnetic wave or light propagated in. They believed that this medium was sort of a gelatin-like material that permeated all things in the world. And so in closing this out, we're going to focus on Michelson and Morley here. And I'm going to start off by explaining the experiment depicted by this optical setup here. So basically, the way that what this is called is a Michelson interferometer. And the way that it works is that you have a monochromatic light source or a quasi-monochromatic light source, and then you shine the light and it follows a path to a beam splitter, and half of the light is going to propagate through the beam splitter to this mirror over here. Half of it is going to be reflected up to this mirror here. Both mirrors are placed at a distance d from the beam splitter. And now here comes kind of the purpose of using a monochromatic light source. So when you're using a monochromatic light source, i.e. a single wavelength light source, once the beams of light bounce off of the mirror, go back to the beam splitter, and go down to the detector here, where I've highlighted some interference fringes, what you will see is an interference pattern. And so if you were to change the distance d for a monochromatic light source, if you were to change the distance d here, then what you will notice is that this fringe pattern will change. And I'm going to start off by just giving a small depiction of how the interference fringes will actually change. So I can start off here by I'll just kind of call 2 points P1 and P2 along a wave. I'm going to draw a line here. So we're going to do one wavelength here, right? So here you have a crest and a trough, and you complete one full cycle. Now, if you have another wave here that is in phase, right? When I say that this is in phase, then every point on each wave is coincides exactly. Then what you'll end up with is a constructive interference pattern. And what you'll see is that the amplitudes will actually increase. So they add. Now, let's say if the wave was out of phase. So right here, these are two wave patterns that are exactly pi over phase. So 180 degrees out of phase with each other. And so they're following opposite paths. And so if we were to add these together, you would get destructive interference. And what you'll end up seeing is that they average out and kind of flatten each other and cancel each other out. So this is the same phenomena that we would expect to see on the detector here at the bottom. So now, why this particular setup? Why this experiment? You might be saying, okay, Justice, I understand basically what the optics is supposed to do, but how is this supposed to help us detect this luminiferous ether? So I'll start off by writing out the objective. So first off, and sort of the first order objective of this is to detect the ether wind. And so I've denoted the ether wind E sub U, and I also have depicted it here. And so in this particular setup, we're saying that the ether wind is moving to the left. Now, so basically the way that this was supposed to work is that it's supposed to detect a ether wind U sub E. The second thing that we want to see is that we want to observe a phase shift delta phi such that the optical path lengths. I'll just abbreviate that as OPL. And if I were to indicate one particular path as D1 and D2, I'll say that the optical path lengths D1 does not equal D2. So how is this supposed to work? Now, if we were to go from a mathematical perspective, we would assume the following. So we know in physics or in optics or anything that kind of deals with waves freely propagating through space, we denote this free plane wave as such. Where phi of x and t is, we'll say, it's typically proportional to the exponent by 2 pi, wave vector dotted with the direction, plus the angular frequency times time, minus this phase shift, or sorry, if it's moving forward, that should be a minus sign, plus this phase shift delta phi. So if we look at the terms in the parentheses here, we notice that all of these things go to dimensionless units. So, for example, the units of K are inverse meter. We know that the angular frequency has the units 1/2. And so, this delta phi, we can assume to be dimensionless. But we can kind of deduce that this dimensionless term has something to do with the luminiferous ether in the following way. So if we go to a fundamental relation in optics, we know that nu, or the frequency of a particular light beam, is equal to the speed of light over the wavelength of that light. So nowadays we know that c is constant. But what if we were to say that we didn't know if it was constant? So then we could say that this frequency, we'll just say, is equal to some unknown u over the wavelength of that light. Then if we go back to the term here in the exponent, then we know that the angular frequency is equal to 2 pi nu, which is equal to 2 pi of u over lambda. So now, basically, if we were to know in one direction that, so let's say in the direction of, let's just say, I believe it's D2, okay. In the direction of D2, delta phi is 0. We'll say delta phi 2 is equal to 0. But then in the direction of D1, delta phi is not equal to 0. And so what does that mean? That means that if we were to go back to the Michelson interferometer setup, as I mentioned before, if D1 and D2 in term to the light is not the same, then these interference fringes will change. And so therefore, if there's a phase change induced in the direction of D1, then we'll see the interference pattern change how I mentioned before, whether it's constructive or destructive interference. And so we can assume that in the direction of delta phi 1, that delta phi 1 must have something to do with the ether wind. So that's kind of how the experiment worked. That's how you can think about the experiment in a nutshell. And so an analogous way to view this is, assume that you're going on a jog and say that you're going against the wind in one direction, and then on your way home, you're running with the wind. It'll probably take you longer to run against the wind because the wind is legitimately slowing you down. It's applying drag on your body. It's it's not helping you move quicker. And then in the direction of you coming home, the wind is actually helping you. So the energy that you're exerting, instead of applying all that to just your body, the wind is taking care of it. So you're kind of exerting more energy. You might be moving a little bit quicker. So they expected to see the same thing with the ether wind, but this was not the case. So what does this actually mean? This means that regardless, and this is what Einstein deduced, regardless of relative motion between observers, the speed of light is constant. Okay, so what that means is that, if we were to if we were to use the classic Galilean Newtonian relative velocity equation, it would mean the following. So let's say particle P is moving at velocity C in a moving reference frame, and this is an inertial reference frame, and what that means is that the motion of this reference frame S bar is moving with a constant velocity with respect to inertial reference frame at rest. So let's say this particle P is moving at velocity C in moving reference frame S bar. What is its speed? And S, assuming it's fixed. So if we were to use the Galilean velocity relation, we'd use this. So we'd say that the speed of the particle with respect to the reference frame at rest is equal to the velocity of the particle in the moving reference frame S bar plus the velocity of the moving reference frame with respect to the reference frame at rest. So it's the velocity of the particle to the ground observer, or the fixed reference frame, is equal to the speed of the particle in the moving reference frame plus the speed of the reference frame with respect to the fixed reference frame. The way that you can view it is that if I'm watching a train go by and somebody's running on the train from one cart to another, in the train, they're moving at one velocity. But to me on the ground, I have to kind of look at the full picture and say that, well, they're moving relative to the train and the train is moving relative to me. So that is how I have to account for the full velocity. But if UPS bar is equal to C, then by Einstein's comment here, regardless of relative motion between observers, the speed of light is constant. Then we'd have to see this. But how is that supposed to work? So this right here is kind of what gives rise to a lot of fundamental questions and exactly, what are we supposed to do with this new assumption that we're making if we don't believe that it fits any of the relations and equations that explain mechanics as we know it. So with that being said, I'm going to end the video here, and we'll start the next video explaining Einstein's fix on relative velocity. Thanks. See you in the next video.